basically a stair-stepped beam that goes down. They're chock full of rebar. So this is an example of a raker coming down. What these do with these stair steps right here is they hold the precast that the seating is now sitting on top of. So as you can see, the dead load alone with nobody on it is immense. When you put live load on it and you get this arena full of people moving around, jumping up and down, cheering, the live load is even greater. So these rakers have an ungodly amount of large rebar in them and very little on post-tension cable. So the engineer on this job kind of strayed away from PT cable and was a lot more a fan of large bar and heavy congestion. So our first feat to conquer was how to get all this rebar in here and get it correct. At the end of each one of these, there's something called a head plate that's basically a massive embed that's got welded rebar to it. So we had to set that embed down in the bottom of this raker with rebar coming up, and then go in and tie in all the rest of these stirrups coming up, all the bands around it, and tie everything inside of this form. We would leave one side open as we did it, and then close up the forming system. So CapForm has, they were our concrete contractor out here, they have kind of a unique shop that builds their own formwork in-house. And that was a really big help on this job as well, is that they were able to ahead of time customize and build the forms for the unique beams and structures that we were building out here. That really helped speed things up rather than the amount of time we would have to spend trying to build something that could hold this head pressure of concrete going into it out of plywood and 2x4s. So we've got unistrut and metal structure holding our formwork together with a slap a piece of plywood in it. Throw some bolts through it, buckle it together, we're ready to pour. So we did, again, another mock-up. We did structural mock-ups out here as well for our benefit, more so than just architectural mock-ups for selections. So we built one of these, actually a couple of these rakers over by our job trailers. Built a full formwork, column system, foundation, tied all the rebar in there, and then we used several of them to select what kind of concrete worked best to get good consolidation. So we also not only had to figure out how to build it, but we had to figure out what kind of concrete would reduce our honeycombs and reduce voids. So once we got that hammered down, we worked on the rakers going up as we poured slabs. Once we got up to the level we call the low roof, which is up where you see this green band going around the building, we got to the plinths. This is a plinth. So this plate right here is another one of those. It's about 1.5 inches thick, and it's got welded rebar. All this purple rebar is welded to that plate. We would set those in place with a tower crane. We would have to get them within 1/8 of an inch, plumb and square. So we had to shoot every corner of it multiple times, and every time we set another one, we had to come back and check the one before it and make sure. Because the tolerances of how this roof goes in are so minimal that we had to basically be perfect. So setting these multi-thousand-pound plinth DBAs, they call them, with welded rebar on them was a huge feat. So we did a mock-up of this right here as well. The first mock-up we did, as you can see, was through Revit, because all we had was about 20 cut sheets like this on the floor plan in 2D. So we went on to Revit and we built it in the model. And then we took that model and we built a 4-dimensional model so we could see what order the rebar would go into it as to get it built, because it gets so congested that there's a spot, if you do it out of order, you can't get back and get the rebar in there. Once we got these plinth mock-ups built out by the job trailers again, we did the same thing, testing types of concrete to use. We used a concrete that did not measure slump, it measured spread. So it had a 27 to 31 inch spread on it, was our kind of our sweet spot, where we would not have honeycombs or voids in our concrete. So essentially it's pea gravel, paste, plasticizer, water, and it looks like soup. So you would set it on a piece of plywood and let it go, and you would literally measure the diameter of how much it spread, because you didn't have a cone like you would when you're slumping normal concrete. So you had a pancake on the floor. And then we would check it every load on the ground before we would bucket it up. And so while we're pouring slabs, at the same time as a slab pour, we would be bucketing concrete into these plinths, getting our basically self-consolidating concrete in there. So we did pretty good. We had, I think, one spot on the entire job where we had a plinth with some voids in it. We were able to repair it from underneath. Question?
I was curious if you had to send back any concrete, how many loads of concrete were rejected?
I had to send some back, but with Tarrant Concrete, they've got a guy who's their chemist who helped us really come up with the mix designs, and I mean, he was amazing. We really hammered it out. He's a top level guy who was coming in at 10 o'clock in the morning or 10 o'clock at night, helping make sure that all these mixes were good, watching QC. So really, we had very minimal on the concrete that we had to send back, as far as not being within tolerance of what we needed it to be. The only time that we had a void was because our pumping concrete had slipped over down into this bottom of this beam form for the plinth, and the larger aggregate had blocked the self-consolidating from getting to where it needed to go. So it was actually just an issue of placement getting in the way.
What PSI was it?
This was 9,000 PSI. So you've also got bonded and unbonded post-tension cable running around what we call the compression ring. So it's basically a giant rubber band around this whole building, because when the roof got deloaded, we had shoring towers up in here, 2 massive towers from the ground all the way up holding it. Once we took the shoring towers down, the weight of this roof pushes down and pushes out on the structure of the whole building. So that brings me over to this board. So once we got all of these plinths poured, tested, checked the height of them, the plumbness of them, the squareness of them, we then started erecting trusses. Once we got the trusses up, we had one of the biggest lean practices we did out here was the engineer gave us a design for the roof, and we had no way to build it. And we developed a playbook that literally talked about every bolt, every nut, every picking point of every truss. It told us exactly where to put our rigging on the trusses to lift them so that they would lift. I mean, as you can see, they're pointing like this. So we had to lift it so that it was at the right angle, so that when we set it, it was right where it needed to be. So everything was calculated ahead of time. We went through, literally we have like an 80-page book that shows the exact order of every truss going in and every bolt going in, and how to tighten them and when to tighten them and all of that. Bosworth was our steel erector. Between them, us, and the engineers, we really put together a kind of a foolproof plan to get this roof up, and we did it in a record time. Once we got it up, we put field engineers here around. We grabbed almost every field engineer we had in Dallas-Fort Worth, and we put them with laser scanners all around the perimeter of the roof structure on the concrete. And we did laser scans of the entire roof system. And when we had these shoring towers out here, before we deloaded them, we checked everything of where it was supposed to be, and we weren't supposed to. The engineer, I think, was assuming up to a 3-inch drop. We made sure everything was good. When we deloaded the shoring towers, we had less than an inch in deflection. I believe it was under half an inch, if I remember correctly. So very, very minimal deflection. Our roof essentially stayed right where it was when we deloaded it. So that was a big feat for us, and we were able to basically go back and rescan everything and check every single point of this roof and make a heat map of what did and didn't move and how much it moved. But we were with flying colors above tolerance everywhere that we were at. Didn't have any failure with the plinths or any of the welds or bolts or anything. So very intensive collaboration between the steel erector, the structural engineer, and us as well. Developing logistics, developing the quickest, safest ways to put this thing together, and then figuring out a way to use technology to help us check it. Because I mean, if we were sitting here trying to stick poles up on that thing with a level and check if this roof was instructed, I mean, we would have been here for another 10 years trying to do that. So we did it in minutes when it could have taken months. So that was, all of this together helped us be in the position that we're at now, to be a month early turning this building over, because we knocked out our structural schedule on time. And we had a very, very aggressive schedule. We were pouring anywhere from 500 to 2,000 yards of concrete a day.
Yeah, we poured 86,000 yards of concrete in 11 months.
Yep.
1,000 piers under the building. We worked on piers forever, up to 60-inch diameter, 60 foot deep. We had, what, 6 rigs running?
6 rigs running.
Did you mention the deck? We've got a really special deck that was made for this building. It's an epic acoustical deck. One of the things the owner didn't like about American Airlines Center over in Dallas, when you go in that building, you see these big acoustical lapidary panels hanging from the, and he really wanted this structure exposed and thought that they were just a big distraction. So I think it was $1 million or $1.5 million ad to use this epic acoustical deck, but it's all perforated and the webs are filled with an acoustical material that absorbs sound. It has the same effect of the lapidary panels, but it covers the whole entire roof.
It's
So,
one of the highest dollar roof systems you can put on a building. But
and architecturally, the design team wanted a very ornate looking. They didn't want to have big chunky members up there, and that ended up being one of our big challenges, hurdles that we had to overcome, because this light structure imposed a lot of additional reinforcement plates where these members connect to these plinths that Eric talked about, that we did virtual mock-ups and physical mock-ups of these plinths that the trusses land on. The reinforcement of the connections to reach the forces that were imposed on these caused a lot of re-engineering, and we had basically a 1 month, 6 month hiccup in the fabrication of the trusses. That was one of our biggest recovery challenges in the schedule. Like he said, we got fabricator back on track, got the structure put up on time, so that allowed us to get the roof on time, get it dried in, get the air conditioning on, get the finishes started. So that was a huge thing to overcome.
got started late and finished early.
Yeah.
At the time when we were doing structure, we had well over 1,000 employees on site working at that time.
We did.
We did. We still had to come back and do touch-up. We had a high access company out here doing specialty painting on them, but we did bring them on site pre-painted.
The fabricator, none of the fabricators that did the job really wanted to do that, because you know their concern was the erector's going to screw it all up, and then I'm going to be having to touch it up. But we looked at with the kind of white colored deck above there, and we were picturing just the access to paint all this in place and not get it on the deck, and it was just well worth painting it at the shop and then having the touch up
Time savings
later.
for sure too.
Oh, absolutely. And yeah, everybody, this is the look at some of the ornamental metalwork on this bar and the stone, and just, you know, indicative of the finishes in the whole building. It's just so really incredible that Mr. Bass was willing to
Pony up.
pony up.
No pun intended.